Good morning to all of my students. Myself, Mr. Dibyendu Mondal, Assistant Professor of Mechanical Engineering Department of Greater Kolkata College of Engineering and Management under JIS Group. In this pandemic situation, I am delivering my lecture through online mode and my video is uploaded in YouTube. Good morning. Today, I am discussing about hydropower development in India. Hydropower is a renewable source of energy which entails any intrinsic advantages. In India, the scope of water power development is tremendous. The first hydropower station in India dates back to year 1897 when a small power station of 200 kilowatt capacity was constructed at Darjeeling. Since then, many big and small hydropower stations have been installed in the country. Total hydro potential in our country is estimated to be equivalent to about 75,000 megawatt at 60% load factor, of which only about 20% has been exploited so far. Actually, state name and power plant install capacity. Andhra Pradesh, here the install capacity 114. Muchakand and Upper Ceylon 120. In Assam, whereas this is 54. Gujarat 300. Ukai. Himachal Pradesh, Bairusuel, that is 200. Okay. Jammu and Kashmir 270. Karnataka, that is the Tungabhadra 72. Okay. And another one is the Manipur 70, Odisha 270, like that, and Tamil Nadu, Uttar Pradesh, Rajasthan 1 by 1. Although the present utilization of hydropower in our country is relatively small, with the present tempo of development and need for power resources, it would not be long before the available potential is fully harnessed. Hydrofield provides immense scope for sophisticated study requiring application of modern mathematical and operational research technique with the help of computers. The following data relate to a proposed hydroelectric station. Available head, so that is equal to 28 meter. Catchment area 420 square kilometer. Rainfall 140 centimeter per year. Percentage of total utilized, rainfall utilized 68%. Penstock efficiency 94%. Turbine efficiency 80%. Generator efficiency 84% and load factor equal to 44%. Calculate the power developed. Suggest suitable machines and specify the same. Actually, head available H equal to 28 meter. Catchment area A equal to 420 square kilometer. Rainfall 140 centimeter per year. Rainfall utilized H 68% of the total rainfall. That is equal to 0.68 into 1.4 meter per year. Penstock efficiency NP, that is equal to 94%. Turbine efficiency 80%. Generator efficiency eta G, so that is equal to 84% and load factor equal to 44%. Power developed, actually quantity of water available per year A into H, so 420 into 10 to the power 6 into 0.68 into 1.4. So 399.84 into 10 to the power 6 meter cube. Hence, the quantity of water available per second Q equal to 399.84 into 10 to the power 6 divided by 365 into 24 into 3600, that is equal to 12.6 meter cube. So P equal to eta 0 into WQH, where eta 0, that is the overall efficiency, eta P, eta N and eta G. P is equal to eta P, eta L, eta G into WQH. So that is equal to 0.94 into 0.8 into 0.84 into 9.81, 12.6 into 28. Machines to be used. Total rating of generator, that is equal to 2186 divided by 0.44. After calculating, you get 4968 kilowatt. Providing two machines of equal rating capacity of each unit, that is equal to 4968 divided by 2 into 0.84. So that is equal to 2957 each. As the available head is low, Kaplan turbine are suggested, each having a generating capacity. The following data is available for a hydropower plant. Actually available head, so that is equal to 140 meter. Catchment area, that is equal to 2000 square kilometer. And annual average rainfall, so that is equal to 145 centimeter. Turbine efficiency equal to 85%. Generator efficiency equal to 90%. Percolation and evaporation losses, that is equal to 16%. Determine the following power developed. Suggest the type of turbine to be used if runner speed is to be kept below 240 rpm. Head available, so that is H equal to 140 meter. Catchment area A equal to 200 square kilometer, so that is equal to 200 into 10 to the power 6 meter square. Annual average rainfall, H equal to 145 centimeter, so that is equal to 1.45 meter. Turbine efficiency, that is equal to 85%. Eta G, that is equal to 90%. Percolation and evaporation losses. Actually power developed, P, A into H, 1 minus Z. So 200 into 10 to the power 6 into 1.45 into 1 minus 0.16. 2.436 into 10 to the power 8 meter cube per year. So Q is equal to 2.436 into 10 to the power 8 divided by 365 into 24 into 3600. Okay, so that is equal to 7.72 meter cube per second. That is the discharge, 7.72 meter cube per second. Now P equal to eta 0 WQH. Actually eta T and eta D into WQH, so 0.85 into 0.9 into 9.81 into 7.72 into 140. That is equal to 8111 kilowatt or 8.111 megawatt. Type of turbine to be used. The type of turbine, actually specific speed ns, that is equal to n root p h to the power 5 by 4. So 240 root over 8111 divided by 140, 5 to the power 4. So that is equal to 44.28 rpm. Single Pelton turbine with 4 jets can be used. Further, Since head available is large and discharge is low, Pelton turbine will work satisfactorily. Now another one problem. Name the common type of prime mover that are employed in a hydroelectric power plant and discuss the factors that govern their choice. A hydroelectric station is to be designed to operate at a mean head of 205 meter and supplied from a reservoir lake having a catchment area of 100 kilometer square. With annual average annual rainfall of 125 cm, of which 80% is available for power generation. The expected load factor at the plant is 75%, allowing a head loss of 5 meter and assuming efficiency of the turbine and generator to be respectively 90% and 95%. Calculate suitable megawatt rating of the station. Comment also on the type of the turbine to be installed. The following three different types of hydraulic turbine are used as a prime mover in hydroelectric power plant. Actually, Kaplan for heads lower than 30 meter and for variable load operation, fixed vane propellers are used for heads less than 70 meter. And for fairly constant load operation, actually Francis turbine used for head from 70 to 500 meter. It is reaction type turbine and mostly used inward flow. The efficiency of Francis turbine at a full load is high. It is designed for higher speed. Pelton wheel used for heads more than 500 meter. Pelton wheel is invariably mounted with a horizontal shaft and has low number of revolution per minute. The limiting power output for a Pelton wheel is of the order of 65,000 HP. Gross head 205 meter. Catchment area 1000 km square. Average annual rainfall 125 cm or 0.125 meter. Load factor 75% or 0.75. Loss of head that is equal to 5 meter. Eta T that is equal to 90%. Eta G that is equal to 95%. Water available during the year 1000 into 10 to the power 6. So 1.25 into 0.8. 10 to the power 9 meter cube per meter cube. Quantity of water available per second 10 to the power 9 divided by 8760 into 36000. That is equal to 31.7 meter cube per second. Average power produced P equal to WQH eta T eta G kilowatt. So 9.81 into 31.7 into 200 into 0.9 into 0.95. So that is equal to 53177 kilonewton. So 53.2 megawatt. With a load factor of 75%, overall capacity of the station for which it should be designed 53.2 divided by 0.75, so that is equal to 70.9 megawatt. So the type of the turbine for a head 200 recommended is Francis turbine. Now Discuss the functions of surge tank in a hydroelectric power plant. What are the pump storage plants and where are they used? What is the differences between the runoff river plant and runoff river plant with pondage? Actually, the data are given. The daily load curve 12 meganewton 5 am and 100 megawatt 5 am to 8 am 120 8 to 12 250 and 12 to 1 100 1 pm to 5 pm 250 megawatt 5 pm to 9 pm, so that is equal to 350 megawatt 9 pm to 12 mn, that is equal to 150 megawatt. It is proposed to install a runoff river plant with pondage and steam plant is supplying the above load. The runoff data indicates that a flow of 50 centimeter cube 50 meter cube per second is available. The head is 90 meter. Hydro plant efficiency is 90% and transmission losses 5%. Determine the capacity of hydro plant and the steam plant. The steam plant is located near the load center. Surge tank in a hydroelectric power plant is an open tank which is often used with the pressure conduit of considerable length. The main purpose of providing surge tank is to reduce the distance between the free water surface and turbine, thereby reducing the water hammer effect on penstock and also protect upstream tunnel from high pressure rise. It is also serves as a supply tank to a turbine. When water to pipe is accelerating during increased load condition, and as a storage tank when the water is decelerating during reduced load condition. Now, the pump storage power plant essentially consists of a head water pond and tail water pond during the off-peak periods of an interconnected power plant system consisting of steam and pump storage. The water from the tailwater pond is pumped with the help of a pump using extra energy available from the thermal power plant. During off-peak hours, with surplus available energy during off-peak period, energy is stored in the form of hydraulic potential energy by lifting the water from lower level to upper level. The same stored hydraulic energy is used during peak load period by supplying the water from the upper basin to the water turbine through the penstock. These plants are used wherever base load station or thermal station and water is also available for hydro generation. Now, runoff river plant without pondage does not store the water and uses the water as it comes. This plant has no control over the river flow. Therefore, water is wasted during the low load and high flood condition. During dry season, the capacity of the plant goes down due to the low flow rates of the water. The utility of these plants is very less compared with other plants due to non-uniformity of supply and the lack of assurance for continuous constant supply. Okay. Last, if you like my video, you have to subscribe. Okay, thank you.